Good evening, one and all. A warm welcome to Jawaharlal Nehru Planetarium here, and also welcome to Coffee with Curiosity lecture series. As you know, Coffee with Curiosity is one of the flagship program held here at Planetarium, which is organized by ICTS. Through this Coffee with Curiosity program, ICTS is bringing eminent personalities and also very interesting science topics to general public. So it has been welcomed by many science enthusiasts, and also it has encouraged many to participate in this kind of science programs. So we are fortunate to have ICTS collaborated with Jawaharlal Nehru Planetarium. Today we have a talk about the imaging story from black holes to MRI by none other than Professor Rajaram Nityananda. So I now request Professor Samuel to introduce the speaker. Sir, thank you.
Friends, it's a great pleasure for me to introduce Rajaram. So Rajaram is presently at the ICTS-TIFR, which is in Hesarghatta, which deserves a visit if you haven't been there. So Rajaram's interests are very wide. I met him first about maybe longer than I care to remember. 1977, I met him first. And he has a wide range of interests across optics, general relativity, condensed matter, and astrophysics. He's a mine of information on all these topics and many others. Let me also say a few words about the ICTS. This is one of the outreach programs organized by ICTS. In addition to outreach, ICTS also has a presence in doing advanced scientific research at an international level and also teaching at the PhD level. We also have we organize discussion meetings at ICTS to get people from all across the world and to help develop the local expertise in these areas. Now, coming back to Rajaram, apart from his numerous interests in physics, he's also a very good table tennis player. Today, you'll notice that he's going to talk a lot about spin. He'll have many spinning things, and it'll make your head spin. But if you challenge him to a table tennis match, you'll be more spinned against than spinning. Rajaram.
Thank you, Anand, and the people at the planetarium. It's been a very long time since I've come here, and it's great to see that it's flourishing and that it still attracts people who are interested in this range of topics. And thanks, Sam, for introducing me and leaving out many things that he knows about me, which he could well have said. Okay. So this talk is about images or pictures, right? We live in an age of pictures, so you can use your mobile to send pictures all over the place. So it's worth reminding ourselves that this is a very old tradition of mankind. So I thought, before getting to all these modern topics, okay, is there a reason why it's not changing? Maybe, does it need to be turned on? Okay, thank you. Yeah, for example, Sam did not say anything about my experimental skills, right? Right. So this is the earliest picture of which we have a record. It's a picture of a pig. It was found in Indonesia, and nowadays with modern technology you can find the date. It's apparently 45,000 years old. So human beings communicated with pictures, and these people must have reached Indonesia. We know that all humans started from Africa. On their way, they probably passed through India, left a few behind, and so this one is Bhimbetka in Madhya Pradesh. You can see that it's by this time a thriving society. So anyway, that's just to introduce the theme of pictures. Now I have advertised black holes because that's a sure way of increasing the size of the audience, right? And I have advertised magnetic resonance, but I'm going to start with another topic And the reason for linking these three topics is that you will see that the principles are all interrelated. They are not identical, but they are interrelated. So, I am going to start with good old X-rays. Most of you must have been X-rayed for some reason or the other. Maybe you, right. The 1901 Nobel Prize in Physics was given to Konrad Wilhelm Röntgen, a German. They still call it Röntgen rays, they do not call it X-rays, right. And this is the first X-ray which he took. You can guess from the wedding ring who the subject was. It was his wife, Bertha Röntgen. But the point I would like to make is that what you see as black in this picture is what you would normally see as white in the normal medical X-rays you are used to. It's just a positive print. So, the black regions are actually the regions where the X-rays have been absorbed. They are not falling on the film, okay. And you can see that the bones are like that and the wedding ring is very much like that. So, basically when you take an X-ray, you are mapping out the ability of the material to absorb the X-rays, okay. And that ability simply depends on the number of electrons, okay. So, calcium which is there in the bones has some 20 if I remember right, and gold has very much more. So, that is why it is blocking all the X-rays, right. Whereas, the soft tissues of the hand which you see between the bones, which are mainly water, right, they are blocking the X-rays a little bit, but not that much, okay. But the thing to remember is that this is really a two-dimensional picture. Now, a hand is a fairly flat object, okay. So, not that difficult to figure out if there is a fracture somewhere there. But suppose I fracture a rib and they take an X-ray, the back ribs and the front ribs will fall at the same point on the image, and how will the doctor figure out? Of course, doctors are not stupid. When they write the X-rays, they say AP and lateral, and AP is doctor jargon for anterior posterior, which means front and back. So, they do an AP and lateral and they figure out what is happening to your knee or something. But suppose you are more ambitious, you want to map out in 3 dimensions the distribution of all these electrons, right. That is possible, and that is the CT scan. Okay. So, fast forwarding from Röntgen's wife's X-ray, I do not know who this person is, but you can see a lot of slices. The top left corner, let me see. Yeah. Is clearly a slice through the nose, and you can also see the 2 eye sockets, and then as the slice keeps moving up, you see all kinds of things, fine. But I can assure you that no animals or humans were harmed in the process of taking this. The person was not sliced, but the slicing was achieved by a technology which I am going to describe to you. So, this is what is called the CAT scan, and the C actually stands for a computer, because we will see that you not only need a nice instrument, you also need interesting mathematics, and mathematics which can only be implemented on a computer, which is why it took so long to develop this technique. So, today you can actually have a 3-dimensional map of a tissue, but of course biased towards electrons, and we will come back to this. If you want to see the soft tissues, then you need something else. Now, the problem that I explained to you is illustrated in this picture. You have the source of X-rays on the extreme left of this diagram, you have the rays, and that very rough outline, think of it as the skull of a person with a nose on the right, and you can see that every point on the film will register the absorption of X-rays along an entire line. So, whatever you see at one point on the film does not tell you where on that line the absorption is happening, okay. It only tells you this is the total absorption. Likewise, you have the total absorption through all these lines. So, it is a kind of the film, of course, in this case I am showing you a slice. So, the object is 2-dimensional and the film is 1-dimensional, okay. Now, so how are you going to find out where the matter which is absorbing the X-rays is located on this line? So we already know the answer from, you have to take a different view. You have to look at it from different angles, okay. So, this is the entire mathematics of this talk. So I am saying this because I think Stephen Hawking says in one of his books, his publisher told him that for every equation you will lose half your audience, okay. Now there is no. So this is a simplified version of the problem of reconstructing a two-dimensional object from one-dimensional scans, okay. So I have just written down numbers 5, 6, 7, 8. Think of them as the number of electrons in those boxes. Now if you send the X-rays horizontally, and then what will the film show? The film will show 11, 5 plus 6, and it will show 15, 7 plus 8. If you send the X-rays vertically from the top, it will show 5 plus 7, 12, and 6 and 8, 14. So now it looks like you have 4 measurements, right? Now, of course, the whole idea of computed tomography is you don't know what is inside to start with. You are only given these different views of the object. So we now have 2 views, 11, 15 and 12, 14. 4 numbers. So you should be able to find out the 4 numbers which are sitting inside the square. Alas, it doesn't work that way because here is another set of 4 numbers, right. Basically you can see that I have added 2 to the 2 diagonal numbers, 5 and 8 have now become 7 and 10, but I have subtracted the 2 from 6 and 7, they become 4 and 5. But you can see that the row totals and the column totals are still the same, okay. So this illustrates one of the pitfalls. Even in this case, 2 views are not enough, okay. So you need a diagonal view, okay. So 5 and 6, 5 and 8 add up to give you 13, and now this other solution gives 17. So now you can distinguish which one is correct, okay. So I would just like to make the general point that again there may be 2 kinds of people in the audience, those who loved simultaneous equations and those who were so scared by them that maybe they stayed away from mathematics after that. So we are talking of a case of solving simultaneous equations for the distribution of absorbing matter inside this slice, and the unknowns are the amounts in these different regions, and the known quantities are what you measure in these different views, okay. So I think it's this general principle that I would like to bring home to you. So you need enough views to get the full details of the image, and if we don't, you will have to use some guesswork or something like that, okay. So here is a CT scanning machine. I sincerely hope not too many of you have had to go through this, because usually that happens, when you're having some health problem. So what's clearly that bed which you see is for the patient to lie down. They've even provided a nice pillow if you need it. And then you go into the machine, and what's inside that circular thing is illustrated here. So you have detectors all around. Let me see if I can. Are you able to see the spot? Interestingly, I am not able to see it. So in any case, you see the ring of detectors, and you see a source of X-rays, and it's the source which goes round and round, okay. So at any one position of the source, you will get the total of all the absorbing matter along that line. So by the time the X-ray tube makes a full circle, you would have collected the information on all the lines passing through this object, right. And from that information, with enough mathematics, alright, you should be able to reconstruct what is inside that object. And of course, you saw a marvelous example of these scans. You notice that there is only one ring of detectors. So even if the X-rays go all over the place, you will only get the information from the slice which contains the X-ray source and this ring of detectors. So of course, nowadays I'm pretty sure that the nearest such CT scan may be less than a kilometer away in Anand Diagnostics or something like that. I mean, they're all over the place, right? And so this has now become a very routine technology. But just think that a map of that kind has thousands of pixels. I'm sure we are all familiar with the word pixel, just a nice term for whatever is sitting at some point in a picture, okay? And you have to solve all these equations, and that became only practical when we had computers. So the C in CT stands for computer. It's either computed tomography, or in the old days it used to be CAT, computer assisted tomography, okay? So this won the Nobel Prize for Medicine for Hounsfield, who actually was not in an academic lab. He worked for a medical imaging company called EMI, and McCormack, and this was 1979. Now, although I said I won't, burden you with the mathematics behind it, it's still nice to, when was that mathematical principle discovered? So you ask what the mathematical problem is. Oh, okay, thanks. Yeah, that's terrific. So the mathematical problem is given the sum, or because it's continuous, you can use the word integral, right, of the density of absorbing matter on all the lines passing through an object, can you construct it, okay? Now, around the 1970s, many people thought about this problem, but it turned out that a mathematician, so ideally the photo of this person, he's called Radon, is not noble gas in the periodic table, it's the name of this gentleman. He's Johann Radon, Austrian mathematician, okay? And for his own private reasons, because 1917, right? So there were no CAT scans at that time. So he wrote a paper called On the Determination of Functions from the Values of Their Integrals on Certain Manifolds. So if you write a paper with a title like that, the likelihood of someone picking it up later and saying, oh, here is the principle which I want to solve the X-ray problem. So that's the reason why his work was neglected. The other reason is, of course, he didn't write that. This is what he actually wrote, okay? All right. But today, this mathematics is called the Radon transformation, which allows you to go from the values of all these integrals of sums along these lines to the two-dimensional distribution. Now, one of the people who rediscovered this, and he definitely had in mind, you look at the title, it says mathematical theory with application to three-dimensional radiography. Radiography is the same thing that we've been talking about, and electron microscopy. So that is G.N. Ramachandran, and one reason to show you this is he's probably one of the most eminent scientists produced in India post-independence. He is no more, his centenary was observed last year, and so of course unaware of Radon's work, he wrote this paper, and another reason to show this to you is the lovely title that he chose. What you are seeing are shadows, right? And he said, I want to know the substance from the shadow. And perhaps he had in mind this theory of the philosopher Plato, that what we see around us is actually a shadow, and there is some real substance out there which only Plato knows about, okay? So anyway, so this is what in cinema is called a jump cut, okay? So I put in this picture, which you have already seen in the poster for this lecture, to remind me that I should now change the topic from CT scans to radio astronomy, okay? So this is a picture of a radio antenna located in Narayangaon. It also reminds me of the many years, a decade that I spent working for this institute, which was called NCRA, also part of TIFR, and going there almost once a week. Now, if you take an antenna like this and radio waves of wavelength 1 meter, okay, this diameter is around 45 meters, then you can ask, if I look at the sky, will I be able to make out 2 points if they are very close to each other? And the answer is no. There is a simple formula. You can take that 1 meter and divide it by 45 meters. That gives you 1 in 45. So that is a measure of the angle, which is a little more than 1 in 60 would have been 1 degree. So this is slightly more than a degree. So all the sources within that circular region of size 1 degree will be seen as a single source of radio waves. So radio astronomy started with this crippling handicap that because of the long wavelength, they were unable to make detailed pictures of the sky. Okay. But they were able to overcome that handicap, and that's the story I'm going to tell you next. And the story starts well before radio astronomy, starts in the beginning of the 19th century. So this person is called Thomas Young. This is a recent biography of Young, which is called The Last Man Who Knew Everything. And that's a very strong statement. So I will tell you all the things he did, and you can decide whether the title of the biography is justified or not. For our purposes, the most important thing he did was to take a source of light, which was I think a candle, let it fall in a very dark room on 2 very closely spaced holes, and the light spread out from these 2 holes and fell on a screen. And on that screen, instead of just seeing light from 2 holes, he saw bright and dark bands. And this is called Young's experiment. It was a decisive step in the history of physics because he realized that this was the proof of the wave nature of light. Now, wave has crests and troughs, the place where it goes up or the place where it goes down, if you want to think of waves on water, okay. And therefore, if 2 waves fall on some point, if the crests fall on the trough, very good, you will get more of wave, and in the case of light, more of intensity of light. But if the crest falls on the trough, the 2 will cancel, it's positive and negative cancelling, and you will get darkness. So light, falling on light to produce darkness is not something that you could explain by saying light just consists of some particles, which is Newton's concept. So whatever I told you in words is illustrated in this figure. So A is a source of some waves which are shown as these circles. B is also a source of some waves which are going in the circle, and they are falling on the screen. And if you look at a point, if you look at this entire line, if you think about it, this is the place where the crests, suppose you take the dark lines to be the crests and the white in between to be the trough. This is the place where the crests of one wave are falling on the troughs of the other wave, so you see darkness. And this is the place where crest falls on crest and trough falls on trough, and you see bright. So that explains the bands that Young saw. And I like this figure. You can find many better figures on the internet, but the fact is that this is the figure Young himself used to explain the wave nature of light and his experiments to an audience like this one, an audience of the general public in the Royal Institution, which like ICTS and like JNP has had a tradition for hundreds of years now of scientists coming and explaining what they have done to the public. Okay. So this is Young's experiment. Now we are going to look at Young's experiment in reverse. Okay. So the message of this slide is that 2 radio telescopes are better than 1. Yeah. So there's 1 radio telescope, 2nd radio telescope. Each of them is looking at a fairly large patch of sky. But on this patch, if you have different sources of radio waves, right? So if this source sends out waves, they are picked up by both the telescopes. It could be that the crest of one and the crest of the other are received here at the same time, and then you just combine the waves. Especially with radio waves, that's not that difficult to do. You can record the waves on a computer, or you can record them on a cable or TV screen, and if once it's in a computer, you are always free to add them. Okay. So this is Young's experiment in reverse. So now in this field of view of the telescopes, right in the center, the 2 paths are equal. So you get a stronger signal, but here you get cancellation. Then a source here again has a stronger signal, and so on and so forth. Okay. So what does this mean? for the goal. The goal is, each telescope is looking at a fairly large region, and the goal is to find individual sources within this region. In that sense, it's very similar to what we discussed for CAT scans. So this is the same situation depicted in a slightly different way. Okay. So this is the field of view of both the telescopes. So the dark lines, let us say, are the places where the two paths are either equal or they differ by one wavelength, two wavelengths. In all those cases, crests will fall on crust and you will get enhanced signal. Okay. So these are sometimes called fringes. Okay. Now the dashed lines are places where if I put a source, the two will cancel. Okay. So now what have we done? We have taken this entire region and we have kind of combed it, right? So certain sources appear with double the strength, certain sources disappear. Okay. Now, of course, if you take this reading, it's maybe better than getting the total of all the sources, but now you are getting the total with some pluses and minuses. So again, you can guess that some simultaneous equations are involved, which I will not go into in detail, but you can also see this information is not going to be enough. Okay. So how do you get all the information to locate a source precisely? Okay. So for example, if a source gives you a strong signal, it could be anywhere on any one of these lines. Okay. So I already told you that two telescopes are better than one, but it's also true that if the telescopes are movable, it gets even better. Okay. So now if I move the two telescopes further apart, the spacing of these lines changes. Okay. So a source which was on one of these bright lines might end up being on in one of the dashed lines. Okay. So again, I am not going into the details, but with all this information, you can actually pin down which line the source belongs to. Provided you are able to move these two radio antennas to different spacings, let us say along a railway track. Okay. So this technique is called interferometry because the phenomenon that Young discovered is called interference. Okay. So this I have already told you. And the last step which you saw was also needed in the CAT scan is to rotate these lines so that you get different views, and then you can pin down exactly where this source of radiation is, where every source of radiation is. Since we have seen the principle in the case of the CAT scan, so what you now need to do is have these two telescopes on a railway line, move them and take readings and rotate, and fortunately in this case the earth rotates. Okay. So this pattern on the sky rotates, and this brilliant idea, I mean of course it took a decade to implement it, is due to Ryle, who won the Nobel Prize. There will be a lot of Nobel Prizes in this story, and with his student Anne Neville, they did an experiment. So within the field of view, so each of the telescopes looks a bit like what you see here, right? I mean, this receives at a wavelength of about 1.7 meters. So each individual telescope looks at a pretty huge patch of sky. Okay. In fact, in this case, they pointed it to the North Pole. The advantage of pointing to the North Pole that stars in that region, stars or radio sources, can be seen all the time, right? Especially if you are in Cambridge, which is quite far to the north. And then they produce this map which shows individual sources distributed all over the field. Now it's easy for me to say this. Preparing for this lecture gave me a chance to read the original papers, and there's a lot of hard work involved. And a lot of the hard work was because computers were not really highly developed at that time. So the research student Anne Neville had to, put this on paper tape, do various things, go to the mathematics department, beg them for time, get some output, play it on a TV screen, photograph it. After doing all this, they did this. But this was the first demonstration of this principle, that if you have small telescopes which look at a large region of sky, but you can group them in pairs. If you can move them, even better. You can then build up a picture somewhat in the nature of a CAT scan. Okay. Now historically, this technique precedes the CAT scan. It's 1960s. Okay. So now I want to show you the progress of radio astronomy. This is the first such telescope, and the entire region which you're, maybe I should use both hands here. seeing here is about the size of the moon. Okay, I haven't shown the angular scale here. It's about the size of the moon. Okay. So now I've already told you about my bias towards the telescope near Pune, right? So I showed you one antenna, but that one antenna by itself could do nothing. So Professor Govind Swarup and his team put 30 antennas, each of which was pretty huge, and they are distributed over a region of size almost 25 kilometers, and all pairs. So if you work out 30 antennas can be paired in 435 ways. So even without rotation, you would get many of these scans. But if the source was very complicated, you would definitely want to let the earth rotate as well, which means observe for a few hours. And this is the principle behind the giant meter wave telescope. It was one of the many telescopes which were built following the lead by the Cambridge astronomers, which I told you about earlier. And right. So I thought I should, though this is not an astronomy talk, I thought I'd show you one astronomical picture from each telescope, right? So, and besides, the astronomer in this case happens to be a good friend of mine, Dharamveer. He did his PhD in IIA and then came to us in GMRT. So, of course, what you see in color is something called a cluster of galaxies, and it's been photographed in X-rays. That's another story. So, all this is very, very hot gas sensed by X-rays. This is a source of radio waves which seems to be swimming in this hot gas, leaving some kind of trail behind. So, he has studied many such things, both for his PhD and later. So, here is just some same things that I have told you. Now, this is a much more recent telescope, commissioned in 2018. It's located in South Africa. The individual antennas are smaller. They are 13.5 meters in diameter. But as you can see, they have a solid surface, unlike the GMRT antennas. So, they can work to a much shorter wavelength. The GMRT antennas can only work up to a wavelength of about 20 centimeters, right? And there are 64 of them, and more are on the way. One of the important things about a radio telescope site is that there mustn't be too much human activity around it. It was true to some extent when GMRT was built, but still it is in western Maharashtra, which is a prominent agricultural and industrial region. So gradually the amount of disturbance keeps increasing. In this case, this is an international project. So to convince people that this is a good place to build telescopes, they would show pictures of lions going around here, which ensure that there are not too many people who would venture. Okay. So this is called the MeerKAT telescope, and here's a very nice picture taken. Another mysterious kind of radio source has this shape, and this picture actually solved the mystery to some extent, right? So Cotton, by the way, is the name of the astronomer, like Dharamveer. So he concluded from this picture and other evidence that this galaxy, so all the stars are somewhere here, and it's shooting out something this way, shooting out something this way, and then that material is coming back, and then it's being pushed out. Okay. Now, when the pictures were not this good, you couldn't be sure, it was just an X. Okay. So this is 2018, but this is where now the black holes come in. Right. So now EHT stands for Event Horizon Telescope. So Event Horizon is a surface where, in a popular sense, the gravity is so strong that once any object goes in, it cannot come out. Okay. And even light cannot escape, which is why it is a characteristic signature of a black hole. Now, I showed you these radio galaxies which had all this energy coming out from them, and paradoxically, the best model which people have for these objects is that there is a black hole in the center. Now, you think of a black hole as swallowing energy, but it turns out that as the matter approaches the black hole, before it actually crosses this boundary, it becomes very energetic, it becomes very hot, it could have a magnetic field and so on, and before it actually enters the black hole, it can shoot out jets of energy. In a full astronomy talk, someone would explain to you how this happens, which I am not going to do. Okay. So there is a connection with the previous pictures that you saw. Those radio sources were believed to have a black hole in the center. However, this was just a belief. What would be the conclusive proof would be to have an image which was sharp enough to show the region where the black hole had actually swallowed up the radiation, okay. And this was the challenging task which was taken up by this collaboration. Now, I told you that the power of these telescopes increases as you place them further and further apart, okay. And what you are seeing here are telescopes scattered all over the earth, right. Here is the map, and there are telescopes in Spain, telescopes in the US, telescopes in Hawaii, telescopes in South America. And of course, now combining the signals is a little more complicated. You can't connect the places with wires. So they recorded the signals at all these places, and this was a formidable task. So the paper which announced the results from this collaboration had some 340 authors. I'm proud to say I know 6 of them, but because they passed through the Raman Institute and so on. But anyway, so building this image took a long time. The data was taken in 2017. In 2019, they announced that they had actually imaged the black hole. But it's sort of interesting. When the image is the bright region around, which are radio waves emitted by matter which is surrounding the black hole. But the most important part of the image is the dark portion in the middle, where you are not receiving any radiation from that point, okay. Now, this claim has now been examined, the same data have been looked at other people. There are also some lines on this image, but in the interest of time, I will not tell you what they are unless someone asks me a question at some point. So this is the extreme to which forming images in radio astronomy has reached. You remember I told you the wavelength is also an important factor. GMRT had wavelength of meters, and the Cambridge people again had 1.7 meters. Here the wavelength came down to millimeters, okay. And remember, if you want to record these signals and add them in the way that I explained, you have to make sure that there is no disturbing factor. You have these paths from the object to the telescopes. If you don't know the position of the telescope correctly, or you don't know the time correctly at the 2 telescopes, then you will not be able to superpose them in the way that is needed to produce the image. So there were very formidable technical challenges, which I will not even go into, except to say that ultimately the positions of these telescopes on the earth had to be known to an accuracy of less than a centimeter, and the time had to be kept. See, in the telescopes that I showed you so far, GMRT and so on, you had one clock and you could send it to all the telescopes, so they were synchronized. But here you had to have independent clocks, but they had to run in synchronism, again to some fantastic accuracy. So this is the culmination of this journey of radio astronomy in using some of the same principles as the CAT scan in a slightly different way to produce images. Right? So M87 is the galaxy where a black hole was suspected for a long time, and now the angular scale is important. I showed you a picture where the size was that of the moon, and now this is the size of a cricket ball placed on the moon as viewed from Earth. So you can see that the subject has progressed a great deal. Right? So that brings me to the MRI which was promised. Okay. So now I am showing you the first proof of concept image. So this person, you may not be able to read the caption, Paul Latterber, he produced this image which was just of 2 test tubes filled with water, okay. Now one important difference between MRI and X-rays is that in a way that I will explain to you, MRI actually senses protons. So for example, water is H2O and each of the hydrogens has proton as the nucleus, okay. So it's completely complementary to the CAT scan, which shows you electrons, and the soft tissues which had a lot of water didn't show up much in the CAT scans which you saw, whereas MRI has this nice complementary thing. So this was just a proof of concept, okay, and I will be telling you how he did it, okay. but this also won a Nobel Prize in 2003. And both these Nobel Prizes were from medicine, because these developments were immediately utilized in medicine. Okay. Now, this is not the best MRI image which I could find on the internet, but I think it's an interesting one. So, instead of showing you a person with some serious medical condition, this is called functional MRI. So, MRI has now reached the stage where they can take an MRI picture of you as you are doing something, as you are thinking of something. Okay. So, unfortunately, I think a lot of advertising agencies have bought these functional MRI machines. This is what I was told. So that, they can show a person an advertisement, and if the right part of the brain lights up, then they know, right? Now, this is an image of a person trying to pronounce the Russian letter L, okay? Which is, you can see the tongue moving up, and someone should do this for Tamil and Malayalam, because they have 3 L's, right? And which people from other states struggle to reproduce. But anyway, I thought this was amusing, and this is just an example of functional MRI, and anywhere on the net you can find lots of images. So, now the principle, okay? The principle dates from the 1950s, though the application to imaging dates from the 70s, okay? The principle is that the proton, we are all taught that it has a charge of 1. They sometimes don't tell you that it also spins and it also has magnetism, okay? So, every proton in your body has a north pole and a south pole, okay? So, left to itself, magnets tend to align to a magnetic field, like magnetic needles point to the north because the Earth's magnetic field points to the north, right? But now something interesting happens. Okay. Yeah. So, here is a magnet, and it's also spinning, that's important, right? And here's the magnetic field which is trying to pull the magnet and make it line up with the field. But paradoxically, what actually happens is that the magnet doesn't do that. It starts moving in a perpendicular direction. Now, in any other place, I would have to ask you to believe it, but in the Jawaharlal Nehru Planetarium, the equipment to demonstrate this to you is available, and Sam has kindly agreed. So, maybe you should first show it without spin, no, Sam? It just, what happens? Just falls down, right? Because gravity pulls it down. But now you are going to see something interesting. It's not falling down, and although gravity is trying to make it fall down, it's moving in a perpendicular direction. So, this phenomenon is called precession, and it's a characteristic of a spinning object where you try to turn it in one direction and it reacts in a perpendicular direction. A very dangerous way of doing this, which Sam would have also done in his younger years, is if you are riding a motorcycle. So, Sam, I don't know if you did this, but if you are riding a motorcycle and you pull slightly on the right handlebar, the motorcycle turns over this way. Yeah, right. So, anyway, as they say in these advertisements, these stunts are performed by experts and should not be, right. Okay. So, please believe me that when you go and lie down inside an MRI machine, which I hope you do not have to, okay, they have this incredibly strong magnetic field. It's 3 Tesla. Now, 3 Tesla is 1 lakh times stronger than the Earth's field, okay. And these protons, if they are making an angle to the field, they are precessing, and they precess at a very specific frequency, okay. And resonance, the concept of resonance is, well, we all know about pushing a child on a swing, right? The swing swings at a certain period, and if you give 1 push per period, you can build up. So, that's magnetic resonance is something similar. So, these gentlemen, Purcell and Bloch, in 1950s realized that you could take a sample of water and apply a magnetic field, and in the perpendicular direction apply another field which would resonate with this, and you would see this precession. So, this is what happens in MRI machines, okay. Now, what I will do at this point is to tell you what happens in an MRI machine in words, okay, since we are nearing the end of the allotted time. First of all, this field is very strong. So, a statutory warning, all MRI things they will tell you don't enter, empty your pockets, no metal. Now, not just magnetic things, even non-magnetic metal, if it moves in a magnetic field, it induces currents. And one thing is, their concern is it might damage the machine, it will also damage you. Okay. I personally made this mistake of forgetting one item and being pulled towards the machine. So, with that warning, the important thing is that they make the magnetic field vary along the length. So, although they advertise a 1.5 Tesla machine, it will go from say 1.45 to 1.55 Tesla along the length. So, that means these protons processing inside your body are processing at different frequencies along the length of your body. Okay. So, now you look for resonance at a particular frequency, okay, by putting coils and doing proper electronics. So, therefore, you are automatically selecting one slice where the field happens to have the correct value, okay. So, that is the first step, you got a slice, but that is only 2 dimensions, right. Then what you do is, you apply a field in the perpendicular direction. It is called a gradient field. So, again that field varies from the bottom to the top. So, in the slice different things are processing at different rates, okay, and you can change that rate. So, I leave it at that point to say that you can gather enough information by changing all these gradients to, again with similar mathematics to the CAT scan and to the radio astronomy thing, to actually build up the full distribution of protons on this slice. Actually, you can do better. These protons, they get tired of processing after a while, a few seconds, and then they come back and line with the magnetic field, just like you saw would have happened with this wheel as well. So, they can even record that time. So, if you, an MRI scan will tell you, do you want an image of just the density, which is the number of protons, do you want an image of this time? So, very sophisticated. As I said, they have lots of tricks up their sleeve. Right. So, that is sort of very condensed description of MRI, but we have done quite a bit of homework on the CT scan, and it is somewhat closer to radio astronomy, because the effect that you are looking at is periodic, right. It has, so if if this is the slice, you have already selected the slice and you have applied a gradient this way. So, here the spins are going around at some rate, here they are going around at a different rate. So, if you register the signal, again you will have positives, negatives, positives, negatives. So, again I dropped the word Radon transform. Now, if you want to deal with things like this which oscillate, and some of you might want to look up the mathematics, I will just drop this word Fourier transform. So, Fourier is again a French physicist and mathematician. So, if you learn Fourier transforms, you can at one stroke learn all these 3 imaging techniques, okay. So, that is the kind of story I have been wanting to tell you, and I also have deliberately not mentioned many names except the outstanding figures, but I should tell you that there are many people who have worked on these, both in the radio astronomy and in the magnetic resonance and so on. And in RRI there was work on how to reconstruct these images by many people, right. And in fact, even recently Sam and I with a couple of others, or even in this audience, have been looking at the problem of reconstructing the radio image. So, these are active fields of research, but I guess what is completely amazing to me is that the products which have been generated, the CAT scan machines, because they are very expensive, and sometimes people worry that once a hospital has paid so much money for a CAT scan, then they have to keep pushing patients through that CAT scan in order to make up the money. I mean, these are moral and financial questions, but purely as a technology, it is, I mean, even though I have explained the principles to you, I personally find it unbelievable that, people can do such things, okay. Thank you.
Hi, my name is Suraj. See, in CAT scan, we know what is the depth of how like let's say a human body is going and coming back, or you know what is the depth of the slicing. Now, if we are going to apply this for radio astronomy, how do we know the depth as to how far we should be able to go? Yeah.
Okay.
Thank you.
Yeah. So the question, maybe if all of you heard it, is what is the third dimension in radio astronomy? Right? Now that's something I did not touch on at all, because the kind of radio sources I was talking about are those which emit over a fairly wide band of wavelengths. So in that case, it's a little difficult to tell how far away it is. But there is an exception. The same hydrogen atoms, right? If they are in interstellar space, they actually radiate radiation of a very specific wavelength, 21 centimeters. But because the universe is expanding, the further away it is, the wavelength becomes longer. Okay. So the purpose behind GMRT, so now that you asked me, I have to bring in more of GMRT, was to look at various frequencies, and each frequency gives you a certain depth in the universe. So that's the brief answer. The third dimension is provided only for those atomic species which in the lab would emit a very specific wavelength. And as you go further and further away, of course, if you go and sit near it, you will measure the same wavelength, but because it's going away from you, you measure a longer wavelength. Right. So, yes, so people who do this kind of 21 centimeter radio astronomy will actually have a data cube. Right.
So here, there's a cell phone tower right atop the roof of my house, and the TRI email that I recently got says that it deals with some 2G frequencies. So I consulted some good medical literature, and it says that these fields are well within safe limit and do no harm to human beings. But the same literature also goes on to say that more long-term observations are needed. So what's your take on that?
Okay. This is a controversial subject. In fact, one of the first jobs I was given when I joined Azim Premji University was, okay, you have come from a radio astronomy place. So we had to deal a lot with cell phone towers, not as our friends, but as our enemies, because whatever they radiate will disturb the radio telescope. So I learned something about all that. So they took me to the hostel where the students felt that, you know, there's this tower right above them and, you know, what's it doing? So the practical answer, so we went with measuring equipment which came from agencies. There are agencies which will measure it for you. Now the interesting conclusion there, which doesn't answer your question, is that the amount of radiation they were getting from their own mobiles and from the wireless routers in the hostel was more than what they were getting from that tower. So they said, okay, if you don't want that, we'll also shut off your internet and your mobiles. And then of course the students were happy then. But that doesn't answer the question of what are the long-term effects. So if you, again, you know, every now and then someone comes on YouTube and says, I kept my mobile next to the plant and then it withered. But of course, if you make simple estimates of the amount, okay, this much I can tell you. If you look at the amount of energy which is actually deposited in your body, that's calculable, and there is a certain threshold which is given by various authorities, which differs in different countries. Australia is very strict. India, as you might expect, is not that strict. Okay, that amount of energy is negligible compared to even sunlight falling on you. So if you think of it purely in terms of energy, then the argument is that it can't do much damage. But if you don't think of it as energy, but if you think of it as an electric field oscillating at a particular frequency which might resonate with some particular molecule and damage it, but in a way that has not yet been developed by science, that is the kind of doubt that people still have. Some people have. Yeah, but as I said, please do measure other sources of radiation in your home, including your own mobile, your own wireless devices. And if they are more than the mobile towers, you have nothing to worry about. Sorry, that's not a nice way of putting it, but you shouldn't worry about the mobile towers. You should worry about this radiation.
So, for somebody with, let's say, a BSc mathematics level of calculus or and linear algebra and all of that, do you have a good book that will help introduce these concepts without going into like very advanced calculus, but sort of staying with matrices or integrals and differential equations and things like that?
No, that's more than enough. But I cannot immediately think of a book. Okay, I have done a fair amount of teaching in Azim Premji University and so on, and we always warn our students, don't go to Wikipedia. But that's not completely fair, because I myself went to Wikipedia quite a bit to prepare this lecture. So if you want a very concise description, I could send. So can I request you to share your email ID with anyone here? I mean, not with me, I might lose it, right? And yeah, any responsible person. And I can certainly get back to you, as you're looking for something concise, right? Yeah.
Yes, that's right.
But I would say the investment made in learning this Fourier transform theory will repay itself manyfold. Yeah.
What is the advantage you have with radio waves compared to CT scan? Because in medicine, hospitals are replacing CT with radio waves for cancer treatments. Is there an advantage?
Okay, can I think what you're referring to is, I've only read it in a few places, that people have used radio waves for treatment of cancer. Now this is a little different from using radio waves to sense. See, even MRI, by the way, I didn't mention that, but the waves involved are radio waves in MRI, okay? But here this is the opposite. You're actually putting radio waves into the cancer to see whether it will be able to destroy it. My understanding is that this is not a very widespread practice, it's still experimental. There are a few places which offer this. The standard for radiation on cancer still seems to be X-rays. But incidentally, to locate the correct place, a CT scan is very helpful, so that you don't unnecessarily damage non-cancerous tissues. And further, the same principle is also used, the direction of the irradiation, which is supposed to destroy the tumor, keeps changing, so that the tumor is always being irradiated, but the region surrounding it gets irradiated less. So some of these principles are also used in planning irradiation. But I have read about these radio wave treatments. My understanding is that they are somewhat experimental, not completely.
Thank you.
Yeah, I had a question about one of the slides that you showed.
Yeah. Which one?
The one with the green patch and how the fringes sort of shifted as the two sources went apart.
Okay. By the way, I should also thank you for telling me that that patch is green, because I happen to be amongst the 11% of males who are colorblind. So was this green?
Blue.
Okay.
Yeah, so my question is that you discussed how if there was one particular point of light source, that how you would locate it by increasing the distance between the telescopes, and that's how you could do it. But for example, say there were two light sources, and so when you did this increasing of distance between the telescopes, you'd get a plus or a minus or whatever, but they're placed in different places, these two light sources, but they're in the field of vision. How do you sort of deal with that then?
Okay, can I be a little more mathematical now that half the audience is not going to disappear? What actually is happening, think of the distribution of radiation from this as a continuous function, just like Mr. Radon, okay? Now that function is being multiplied by a trigonometric function, sin x. So what the Fourier theory tells you is, if you multiply it by trigonometric functions of different wavelengths, which you control by moving the antennas, then you can reconstruct the original function. So I think that's the most straightforward way of understanding it.
I'd like to continue what the lady asked. Why is it considered that an MRI is less dangerous than a CT scan in terms of the radiation? Is it just the wavelengths of the radiation that's being used, or is it something else?
See, right from the beginning, it's been known that X-rays do damage tissues. In fact, that is used in the treatment of cancers by X-rays. Whereas with radio waves, as I said, the actual amount of energy delivered to you is negligible. Of course, there is still this concern about long-term effects, but apart from that, there is no question that in an MRI machine, of course, you are in this static magnetic field, which of course can play havoc if you have any metal parts on you, but otherwise, again, up to a certain strength, it is believed that it doesn't cause any damage. When I say static, I mean not varying with time. But in order to get these slices, gradients and so on,
you have to vary.
You have to vary it. Yeah. Now, varying magnetic field does produce electric fields and so on. Have you been in an MRI machine?
Yes.
Does it emit very frightening sounds?
Clicking sounds.
Yeah. That is when these gradient coils have to rotate. So, you have to keep changing the field. And when a coil produces the magnetic field and you suddenly change the current, it actually, there's a nice demonstration in Visvesvaraya Museum. You have a coil, the moment the current goes through, it jumps up like that. So, even with the best design, so all those mechanical effects and electrical effects are there. But the consensus is that it's not as damaging as X-rays.
But the question that I was really asking is, in the MRI machine, what is the frequency or the range of frequencies that are
sure.
compared to
there's a simple number. It's 42 megahertz per Tesla. So if you're on a 1.5 Tesla machine, maybe 60 megahertz, which is not that high a frequency. I think 60 megahertz, at 90 you already start getting FM stations and all that, right?
Hi, I have a question about the M87 image that you showed.
Yeah.
I'm asking this because you are an author of the paper, I assume. So in that image, as I remember, the image is not the first initial image that the EHT team released. This is one of the second images which has the magnetic field lines.
Absolutely.
Right. So, and this was formed, this is not the image, that was formed with the same data that they collected at the first run. And how did they get the extra details that they needed for the magnetic field?
Okay, fine. So, I just said radio waves, but if a radio wave is propagating towards you, it has a property called polarization, which simply means it has an electric field. The electric field in the radio wave is what drives the current in the receiver, okay? And if it's going towards you, the electric field can either be in any one in the plane perpendicular to that. So, really to fully specify a radio wave, you need, you can't just put a piece of wire like this, you need two. So, every one of those telescopes actually had two. Now, what they did in the first round, but the polarization is somewhat weak, okay, it's about 20%. So, initially what they did was just process the data from each of these independently. And that didn't tell you anything about the direction of the magnetic field and so on. And then, as they got more confident with the processing and were satisfied that, you know, they can also extract this polarization signal, it took another 3 years. So, yeah, a lot of hard work. So, in general, polarization signals are weaker than the full intensity signals. Yeah.
Just the same picture, like what are those lines?
Those lines are actually the direction of the magnetic field in this matter which is swirling around the black hole. Now, that is inferred. But again, the principle is simple. If you have, say, a magnetic field like this and you have a charged particle, it orbits like that. So, you would then see an electric field polarized like that. That's it. Yes, they are bent, presumably because the matter is rotating at different rates as you go around. As you go further away from the black hole, it goes more slowly, so it lags behind. By the way, the expert on this is a colleague of mine called Pallavi Bhatt in ICTS, so she can probably tell you more. Pallavi Bhatt.
Hi. So again,
or her student who is sitting behind.
So again, the same image. You told that the telescopes need to be the clock that each antenna receives has to be kept in sync. So how did they manage to keep them in sync across the globe? I mean, one is in South Pole and one is in US.
Okay.
And just one second basic physics question. This is like we're receiving radio waves by antennas. Very basic question. Why can't we receive them as photons or conventional image-based telescopes we have?
Okay. So let me answer the physics question first, right? you know the energy of a photon is proportional to its frequency. So if you take optical frequencies, that energy is in the range of several electron volts, okay. So when it falls on a CCD detector, whatever you have in your mobile phone, it's able to make the electrons jump from one level to another, and then you can pull it out. Yeah. However, radio waves, the frequency is orders of magnitude less. It's a very tiny amount. So even if you had a material which that small gap, you would have to cool it to a very, very low temperature so that only the lower level is populated. So basically your question is, why not a quantum detector for radio waves? And the answer is, number one, it's very difficult. Number two, it's not necessary, because you put a piece of wire and it drives a current and you can read it off. Okay. So your other question was about the clocks. Okay. There is again a whole story about the development of clocks. So these clocks, time all over the world is kept by something called cesium clocks. There is one in NPL, and of course the one in France. There is an international thing which decides how to keep time. Then these are also connected by GPS. So your phone, I think, keeps time by GPS. So GPS was used at each of these points. It will give you a certain accuracy, but GPS will give you a pulse once every second. But in between, see, the frequency is such that in that second there will be 1 billion cycles of the radio wave. So therefore they need an oscillator which will not lose its accuracy over that few seconds. That is something called a hydrogen maser. Now you build two hydrogen masers, are they identical? Not completely. So there is a whole story behind how these clocks were synchronized and so on. So it's a very interesting exercise. That's all I'll say.
I have one question. So in the CT scan, you had that shadow example, right? The paper that title of the paper, right?
Right.
So there is absorption going on there, right? For the radio waves when the CT scan is getting done.
So where is it going on? Is it?
It is when the radiation is getting absorbed. Yeah. That's the shadow that we are talking about, right? So it is absorbed by electrons.
Yes, electrons in atoms, yes.
Correct, correct. So that is also getting, so there we need to have a photon perspective of thing.
Absolutely.
Right? Because it is happening in discrete form. So my question is, whether radio wave, the question that came about radio frequencies, whether for a given amount of total energy we have more number of photons which are there, which help in, because you have more excitations to do, is that advantage that you get with the radio waves also? I mean, apart from other things, because for given energy you have more photons.
You don't have, for a given, well, both have their advantages. Say, so you know, I mentioned that the optical thing are a few electron volts. By the time you come to X-rays, it's thousands of electron volts. Okay. So So reception of an X-ray is a discrete event, like a bomb going off. Any detector will show it. Now in the radio case, you're right. You have so many photons that it almost behaves like a continuous wave. See, after all, no one asked me, you know, in Young's experiment, he proved that it was waves, right? I mean, Newton said it was particles, Young said it was waves, then Einstein came and again said it was particles, okay, which I didn't bring up. But our modern understanding is that both aspects are there. That is, the way these particles behave in detection and so on is governed by some underlying waves. Maybe that's the best way to put it.
Okay. And then last point. So that absorption that happens, right? Since it is discrete in nature, do you need the energy enough? Do we know what exactly the energy enough needed for the absorption to happen also?
Yes,
right?
yes.
So that
in the early days of X-rays, people studied these things. Okay. So if you have a target of copper, it will emit an X-ray of a certain wavelength, and it will be able to kick out electrons from certain atoms and so on. So all that is well studied. Yeah.
Hi sir, thank you for your talk. I have one question. So all this while, thank you for taking us through the history, right from the history of where we all started and where we are right now. But how do we see this going forward? So what's CT has become the kind of a order of the day where most of the things, especially very widely used in the medical fraternity and thing. But where do we see this going in the near future? Say probably 2 decades or one decade. What's the research that's happening on this side?
My impression is that the CT technology is very mature. In the sense the detectors detect probably 100% of all the photons which arrive on them. So there's not that much scope to make it more efficient. You might have read multi-slice. So I showed you, there the detectors on a single line. So, but since the X-rays source is spraying it out on a bigger area, it makes sense to put detectors on that entire region. So for the same dosage to the patient, you would gather more information. I think that's already happening, multi-slice. People are also trying to reduce the dosage by clever algorithms. That is, can you get away with, giving less radiation to the patient, so gathering less information, but using other information, like all the electrons in the patient are confined in a small region. So that's a kind of dangerous field in which I used to play around when I was young. That is, how do you make images with incomplete information? So that's a direction, but I would say it's a mature technology. We cannot expect dramatic changes. In MRI, again, I'm not an expert, but I had colleagues when I was in Hyderabad who were experts in magnetic resonance. There they expect much more sensitive detection because you're detecting radio waves now. So already, of course, the magnet is cooled and so on, but there are very sensitive devices. And what history seems to have shown is that once a physicist makes some device, there are companies willing to invest money, make it a product, launch it everywhere. So MRI, we may see dramatic improvements. See, it's interesting. No, look at mobile phones. They're getting better and better, but not cheaper, right? For the same money, you get better and better. So I suspect they will still charge you, 10,000 in the hospital, 5,000 in the center, but they'll give you better images. I mean, this is just my guess. Huh?
Thank you, sir.
I just wanted to know, is there any, you mentioned there are improvements, now is there any way we can see the heart blockages using this scan? I saw some videos, they were saying rather than putting probes and finding out the heart blockages, we can do some scans and latest improved scans.
Cardiac CT is a standard technique.
Okay.
By the way, I mentioned atomic number, no? The number of electrons per atom. So, blood already has iron, which is reasonably good, but I think they can inject you with things which have even more power of absorbing electrons. And they don't do a full CT scan. My impression is that when you undergo angiography, they have a source and a detector, and quickly they move it around, get all the views, and the doctor has enough skill to say, okay, there's a block here. Their goal is only to locate the blocks. But I think the cardiac CT, they give you a full 3D. I'm told that angiography is still considered better, which is more invasive, you go in.
Investigating the heart blockages, an ultrasound image enlarged by laser beam, equipment that does that. That you can do away with angiography because the image is enlarged and the doctor can see more clearly. Because angiogram has its side effects. You can get knocked off in the brain.
Okay, I was actually unaware of this new technology. You're saying it involves ultrasound but also laser beams.
Ultrasound, the picture that the ultrasound gives you,
yes,
enlarged by a laser beam, an equipment that does both. The image that the doctor sees is clear. It will clearly show him the blockages instead of doing an angiogram, because an angiogram has side effects and it's kind of primitive because the brain gets affected if it doesn't go very well. So they want to do away with the angiogram by using ultrasound.
See, I am aware of ultrasound, and it is used to study the flow in the heart, for example. they do echo and Doppler and all these things. I didn't realize that the resolution is so good. Resolution being the ability to see small details. So honestly, I may be less well informed than you. I should look it up. Yeah.
So there is an online question by Supreet. He asks, how do you 3D reconstruct from an image, from images?
How do you 3D reconstruct?
Yeah. So
okay.
what's the you have set of images and now you need to have the 3D model. How do you go about it?
Okay. So both in MRI and in CAT scans, the problem is first simplified by concentrating on a given slice of the patient. So the 3D comes by just stacking these slices on top of each other. But in radio imaging, it's actually possible to get the full 3D data by recording the interference between all pairs of antennas, not at one frequency, but at a range of frequencies. So that directly gives you a 3D image, right? So that would be my answer. There are also schemes in, for example, there is something called a spiral scan in CT, where they don't do it slice by slice, you continuously move through. So then they get a single stream of data which gives them the 3D image. So spiral CT is the one thing to look up.
Thank you. I had one question. So, something related to this question. Say, so you said there is a hydrogen, say, I'm just taking an example, which is 10 kilometers away, and it's radiating towards me at a certain frequency. And then I have another object along the same line of sight, and that is say 1 kilometer away. And that is also the frequency that I'm receiving from this nearer object is same at my place, because that is Doppler shifted, and suppose this is, so now how do I know that I'm getting the radiation from the distant hydrogen versus how do I resolve these two?
First of all, I would change the units in your question from kilometers to megaparsecs or something. The distance between galaxies, because this motion is due to the expansion of the universe, and fortunately our little part of the universe is not expanding, right? It's staying at the same size. So only when you look on the scale of galaxies. So, but your question is reasonable. I may have a galaxy which is 2 megaparsecs away, another which is 4 megaparsecs away. If they happen to be on the same line, the images would still be separated in frequency space because of what you call the Doppler shift. The fact that whatever is going away from us will come at a lower frequency.
Yeah, no, but suppose I don't know what object is that. So that is hydrogen, for example. Distant one is hydrogen. Yeah. But then the radiation is Doppler shifted. I am getting some X unit of radiation here. But then in the middle, I have some another object. I am not aware, but that is radiating at that. Some other frequency. Yeah. Which turns out to be slightly Doppler shifted, and at the end I get the same.
But the receiver can separate different frequencies, no?
Okay.
So you can create images at different frequencies, and even though things are in the same line of sight, they would get separated. In the particular case of hydrogen atoms in an expanding universe, I want to make that very clear. In many other cases in astronomy, it's quite hard to find out which is nearer and which is further. You need something where the frequency is known.
Okay, and I had one last question. So, what is the difference between Radon transform and say Fourier transform? Like, where is it used? Like,
the way the Radon transform is written, it doesn't look like a Fourier transform, but it can be derived from Fourier transforms. Yeah, that's right.
Thank you. Thank you. Any other questions? Please raise your hand. I'll bring the mic. I think that's it. Thank you.
Since there are no more questions, I'd like to ask Supurna to present Rajaram with a memento of this talk.
Thank you, Supurna.
And let's all thank Rajaram for a very informative talk. Even if he made your head spin at times with the simultaneous equations.